t-stats, confidence intervals, and p-values. Why statistics? Why statistical tests? The main question we face when doing statistics is how close is our estimate to the true population value? Okay, let's make this a little concrete here. We suppose we work for the census and we want to know what the average income of all people in the US is. We've had this example before, but we can't go out and get the income of everyone in the US and then take the average. What we need to do is take a random sample from people in the US and then calculate an average from that random sample. So the question is, okay, we have the population with, this is everyone in the US, everyone in US, and there's a true mean income in this population, which is denoted with mu y, if the random variable of income is y. And we know we can't sample everyone in the population, so we sample, say, 1,000 individuals, and then we estimate y bar from that 1,000 individuals, and we get an sample average, y bar. Now the question that we want to know is, how accurate is y bar? Accurate in terms of how close is it to mu y? How close is our sample average estimate to the real value? And statistics gives us a way to talk about how confident we are in our estimate of y bar, or whatever estimator we're dealing with. So the sample average y bar is rarely equal to the hypothesized average, mu y naught, because for several reasons. First, the population mean doesn't equal the hypothesized mean. So maybe we guessed wrong. So maybe we guessed our mu y naught wrong. And so this thing doesn't actually equal mu y. Another would be that the population mean does not equal the hypothesized mean, because our hypothesis was right, but the y bar is, this is the population mean does equal the hypothesized mean, but y bar is far from mu y due to random sampling error. Maybe we sampled only the rich people in the US and calculated y bar from the rich people, and it turns out our hypothesis was correct, but our sample was really wrong. And therefore, statistics gives us a way to provide probabilistic estimates of how close our samples are to the true population values. And we have three ways of doing this. The t-statistic. T-stats are formulas used to perform statistical tests, and this is the formula for the t-statistic. We take y bar minus the hypothesized mean over the standard error of y bar. So this thing should look fairly familiar. All we're doing is subtracting a mean and dividing by a standard deviation. So this is a standardized normal random variable, because by the central limit theorem, we know y bar has a normal distribution with mean mu y bar and variance sigma squared y bar. A guess of mu y naught is rejected at the 5% level if it is more than 1.96 standard errors away from y bar. So our rejection rule, we should write this out, rejection rule for the t-statistic, if we get a t-statistic that's, if the t-stat in absolute value is greater than 1.96, we reject with 95% confidence. Why 1.96? Okay, let me draw the standard normal distribution curve here. Okay, what we're really doing, we're taking standard normal distribution curve. Let's say we centered it at mu y0, mu y naught our null hypothesis, and let's say the null is equal to 0. So we have a perfectly centered standard normal random variable. Y 5%. So what's at 1 or why 1.96? What's at negative 1.96? So if we go look up negative 1.96 on the z table, what does it tell us? It tells us that 2.5% of the mass of this curve is to the left of negative 1.96. And by symmetry, 2.5% of the mass of this curve is to the right of positive 1.96. And since we're dealing with a two-sided hypothesis, then we're going to take this 2.5% multiplied by 2, which gives us 5%. And so the area inside here is 95%. So this is a 95% confidence. That's where we're getting the 95% from. Okay, using this to get us a 95% confidence interval. So the 95% confidence interval for mu y is written as the absolute value. The t-stat is less than or equal to 1.96. So we can take away the absolute value, and then we get the second line here. So we get negative 1.96 is less than or equal to t, which is less than or equal to 1.96. We can substitute in the value of the t-stat for line 3, and then with this we can then multiply both sides of the equation by the standard error. So that's this coming over here and over here, and then we get line 4. Then we can subtract y bar from both sides. That's what we get with line 5. And then we're going to divide by negative 1 because we have a negative here. And when we divide by negative 1, the less than or equal signs are going to flip. And that's what we get on line 5. And then we just have a range of values for mu y. So that's what line 6 is giving us. Actually, that's line 7, isn't it? So we're saying mu y naught, the null hypothesis is contained within this interval. Y bar minus 1.96 times the standard error, and y bar plus 1.96 times the standard error. It's more often written as y bar plus or minus 1.96 times the standard error of y bar. The interpretation is that if the null hypothesis is outside this confidence interval, we can reject with 95% probability. So it's the same, we're still getting a rejection rule, but it's the same essentially as what we would have gotten with a t-stat, except now we're getting a range of values that we can say we must fail to reject with 95% confidence. If mu y naught is inside the confidence interval, we fail to reject. We'll do an example of this in a moment. The p-value. This is probably the most complicated one. So where the t-stat, we specified 1.96 as our rejection criteria. We wanted to be 95% confident, so we have not 1.96. The p-value is going to flip that on its head and say, well, how confident can we be? How confident are we? The definition of the p-value is the probability of drawing a statistic at least as different from the null hypothesis as the one you actually computed from your sample, assuming the null hypothesis is correct. For the mean y bar, the p-value indicates the probability of drawing an alternative y bar from your sample that is at least as far from mu y naught as the original y bar. Okay, this is complicated, I know. So let's take this apart. Use an example first. Suppose we have our null hypothesis is the average height of students at CSU is 5'8". Now suppose that I go out and sample 100 students and I get a sample average y bar and it's 5'4". So what's the difference? 5'8" and 5'4", 5'8" minus 5'4". So when I say the difference, or at least is different, we're just dealing with 4 inches. It's a simple difference here. A p-value of 5%, says there's a 5% chance of drawing an alternative average estimate y wiggle, that is at least as far from 5'8". So at least 4 inches away from 5'8", assuming the null hypothesis is true, assuming 5'8" is the true value. This means that it's fairly unlikely that the null is correct, or we would reject our null hypothesis with 5%, 95% confidence. So if we reject the null, we say the average is 5'4" with 95% confidence, that if the true average were 5'8", we would only get a sample average of 5'4", 5% of the time. So if we kept drawing samples from our population and computing the sample average, If we did that over and over again, only the p-value says that if the null is true, 5/8, only 5% of the time will we get a y bar that's 4 inches away from 5/8 if the null was true. So we can fairly safely, or we can reject the null with 95% confidence. We can say that 5/8 is not the true population mean. P-values continued. Smaller p-values indicate we can more safely reject the null hypothesis, right? So if we get a p-value of 0.05, it says we're 95% confident. If we get a p-value of 0.01, then we're 99% confident. Larger p-values make us less certain. Mean we're less certain we can reject the null hypothesis. So a p-value of 50% says there's a 50% chance of estimating a sample average at least as far from our null as the one we estimated, assuming the null is true. Thus, we would fail to reject the null with any realistic measure of confidence. How do we calculate the p-value? Well, first let's do it when we know sigma squared y. We'll never know this in reality because sigma squared y is a population value. Suppose we hypothesize the average of a population is mu y naught, and we estimate a sample average of y bar actual, and we know the variance of the sample average because we know what the variance of y bar actual is. The central limit theorem tells us that when n is large, under the null hypothesis, y bar is distributed with mean null hypothesis and variance sigma squared y bar. We can standardize the distribution of y bar so that it looks like this, and we have a z standard normal random variable. So let's calculate the p-value when this variance is known. Okay, in words, the p-value is the probability of obtaining a value of the random variable y bar further from the null than y bar actual when the null is true. Or in math, here we have the probability of obtaining a value of the random variable y bar further from the null. That's this part here. Or the distance of the random variable y bar from the null. And then we further from y bar than the actual, or further from the null than the y bar actual. That's this part here. So we're just taking the difference, right? That's what we're talking about, the distance from, or a value that's further from. Okay. Then we can take this and, or the greater sign here says this distance standardized, the distance on the left standardized, is greater than the distance on the right. And then we have what's the probability of that happening. Okay, so then we can take the thing on the right, take the absolute value of it. It's already an absolute value, but the negative of the absolute value. So this ends up looking roughly like a t-stat, right? The only thing different is that the bottom is not the standard error. So if this is a t-stat, or if this is a standardized normal random variable, then that means we can go look it up on the z-table. That's what the phi thing is. And because we're dealing with a two-sided hypothesis, we have to multiply this by 2. So really what we're dealing with is again the tails of the normal distribution. The problem is that what we just did depends on knowing the variance of y bar, which depends on knowing the variance of y, the variance of the underlying random variable, which is almost certainly unknown. So what do we use? We use sample variance, the standard deviation, and the sample standard error. So let's calculate the p-value when sigma squared y is unknown. Because s squared y is a consistent estimator of the population variance of y, we can replace sigma y bar with the standard error. So we can replace it with the standard error of y. And so this is just a t-stat now. And this can be written as the p-value is equal to 2 times phi of the negative of the absolute value of the t-stat. So this is just the probability of observing a t-stat greater than the estimated t-stat when the null is true. So if we look at our standard normal distribution curve, and suppose our null is here and it's equal to 0, What this is just saying is, okay, how far out is our negative of the absolute value of our t-stat? So the negative of the t-stat. Suppose we get a t-stat of negative 1.96. We're there. Suppose we get a t-stat of negative 2.3. Then we'd be somewhere out here. And we would look those values up on the z table and multiply by 2. And then whatever we get, so if we had negative 2.3, suppose that we looked that up on the z table and it turned out that was equal to 0.001. We'd multiply that by 2. That would mean we'd be 99.8% confident. I think that should be about correct. Let's do an example. All right, we want to figure out the mean wage of college grads. Right? Suppose we're trying to figure out the mean wage of college grads. Let's make this a little more concrete. We want to know the mean wage of college grads last year. What was their average wage this year? Okay, there's a lot of people graduating from college in the United States in 1 year. Suppose we go out and sample 200 of them. And we take the sample average of those 200 people and we find it's $22.64. We've defined our null hypothesis as $20 an hour. The sample standard deviation is $18.14. That's of the 200 individuals. And the standard error of y bar is this value divided by root n, which is 1.28. So let's calculate a t-stat. The t-stat, remember, is just equal to y bar minus the null over the standard error of y bar. So we plug in y bar, the null, and the standard error, and we get 2.06. So go look up 2.06 on the z table. Actually, we would be going and looking up negative 2.06. But we can also just say, can we reject this with 95% confidence? Remember the rejection rule is reject if absolute value of the t-stat is greater than 1.96. Is 2.06 greater than 1.96? Yes, it is. So we reject with 95% confidence. P-value says, well, how confident are we? So let's go look up the negative of the t-stat on the z table. That's what this symbol means. And then multiply it by 2 and we get 0.039 or 3.9%. And then we can say we are 100% minus 3.9%, which is equal, what, 96.1%. We're 96.1% confident. So assuming the null is true, the probability of obtaining a sample average at least as different from the null as y bar actual is 3.9%. Not likely. So if we went out and sampled 200 other people, the probability of getting a sample average that's at least as far from our null hypothesis of $20 is only 3.9%, assuming that $20 was true, the true population average. So we can reject $20 as the population mean.